In this video, I want to take you through this snake-like game that I've built using JavaScript, and more precisely, JavaScript in functional style, or in functional programming style, so with a focus on purity, small functions, and composability. So as you can see here now, I'm running this snake game in the browser. And you can see also there that I actually crashed. Sorry, my camera is in the way, so I can't really see what I'm doing in this snake game. So, but this is the browser implementation. And because I tried to put the focus on modularity, it was kind of trivial to make one sort of GUI for the browser and then another GUI for the terminal. So if we jump over here to this side, you can see if I just look at where I'm at now, I'm in a folder called Snake where I have a few files. And what we're looking at here in the browser is this web.html file. But what I can also do is I can run this CLI.js file through Node, and then we can play Snake in the terminal. So if we run CLI through Node, you can see that we now get Snake, but in sort of terminal mode. Let me make this a bit bigger. So the X's represent the snakes, the dots are the grid that's traversable, and the O's are the apples that you need to eat in order to become longer. And the interesting portion is, of course, or the interesting part is, of course, that this runs on the same quotation marks engine. Like, we've separated the game engine from the visuals of the game, which is generally what we should do, right? We should separate presentation from the business logic. So my interpretation of most of the Snake tutorials, or actually game tutorials that you find on the interwebs, is that they are focused on just getting a quick version up and running quickly, essentially. But what I want to do, as I tend to do with all of these videos, is instead talk about design. So I'm by no means saying that this is a perfectly designed Snake game. At some point I just said, okay, never mind, let me just drop this, make this video, and I'll leave it to you guys to hopefully improve upon this game and make it even better. Or rather, I should say, improve upon this code and make this code base even more modular and elegant. That would be fantastic. So if you do have comments, please do shoot those in the comments, or if you do fork off from this code base and make changes, please do post your changes in the comments. That would be really interesting to read. But anyways, when we focus on modularity, we can, again, trivially achieve this kind of thing where we have one implementation for the terminal and one implementation for the web, which, of course, if we generalize this notion, what we're talking about here is that you might have a single core and then multiple different implementers of that core, or users of that core. So that might mean that you could have, let's say, a multiplayer portion of your game, or you might expose your game through an API, or you might make an iOS version and an Android version and a web version of your game, and so forth. And now I'm saying game, but actually we're talking about applications, right? So generally what I usually want to talk about is design of programs, is how we keep programs alive over longer periods of time, and how to increase modularity. And so in some sense, then this game is just an example of that. But anyways, you could also just see this as how to build Snake using functional programming in JavaScript. Let's get going. So let me cancel out of the game here, and let me make this full screen. Okay, so again, let me just show you the files that I have in this folder here. So the main Snake implementation is in this file called snake.js. That's sort of the core library, or the game engine in some sense. And then these three files, web.css, web.html, and web.js, that's essentially the web interface for the Snake game. So that's what we were looking at when we were playing in the browser, those three files. And then this CLI.js file, that's the Node implementation. That's what we were looking at up here, right? That's the terminal GUI through which you can play this Snake game. And then finally, this base.js is some base functions. So essentially, when doing functional programming, as I've talked about in other videos, we tend to pass data last, and we tend to have functions that are curried. So we tend to have functions that are partially applicable. But of course, JavaScript doesn't work this way, so that's why I implemented a few functions myself, such as map and etc. And of course, like, if you would build an extensive game, you would probably use a third-party library, such as, for example, ram.js, or another library implementing the Fantasyland specification. But for the sake of this video, I really wanted to keep everything self-contained. I don't want to use any third-party libraries, and this is why we have some code in this base file. But and then of course we have this README file, just because I've put this up on GitHub. And by the way, you can find the link to all of the code in the description. I might have moved it elsewhere, but the link in the description should work. Let's actually start by looking at the web end. So let's start with web.html. So let me open Vim, and then let's open web.html. And as you can see, I mean, this is clearly just any old normal HTML file where we are loading in the style sheet. Here I'm doing some funky stuff. I'll explain that in a moment. But then in the body, we have a canvas setup that's of a size 700 and of a height, or of a width 700 and of a height 500, and then I'm loading these script tags. And maybe people nowadays always load their scripts here and then make sure that the DOM is loaded in the scripts files. I was just lazy and put them here to ensure that when I load this web.js, the canvas has definitely loaded. But yeah, that's a completely different discussion. But anyways, you can see here that I'm loading in the base library, then I'm loading in Snake, and then I'm loading in web.js. So clearly, I mean, this is because I don't have a build system set up, or I don't have a build process set up. So I mean, clearly, if you were building this and actually shipping this on the web, you would probably somehow like minify all of your files into a single main.min.js file, right? And you'd only load that, and that would do everything. So you would construct a single JavaScript file from all of your other JavaScript files. But now this is just a simple example, so let's not bother with that, right? So then we're loading in the base library, and the base library will expose a bunch of globals, or it will essentially define a bunch of functions that are available on the global scope. And same thing for Snake, and then web is the actual machinery of this web implementation, or I shouldn't say the machinery, is the actual main entry point of this web application. And then let me just quickly explain this. I mean, this I do. Let me open up a split here and open up snake.js in order to show you that. So snake.js, because I started with the command line implementation. Actually, from the beginning, I was thinking that I only should do the command line implementation, but then I figured actually it's so easy to make another web implementation, so let me just make a web implementation as well. I'm a big fan of trying to keep it as absolutely simple as possible from the beginning, and this is why I started building this snake.js file, and I started doing it in a sort of step-by-step fashion where I implemented one function at a time, where it's like, okay, this function needs to be able to do this, right? So like if we have a list of snake points and we want to compute the next snake point given a movement in some direction, what would that function look like, right? And then I did that step by step for all of the different pieces, and then I sort of from the ground up built the Snake implementation. But anyways, because I did this, I want to make use of the module system in Node. So you can see here in the end that I say module.exports, and then I export a bunch of actually first constants and then 3 functions. And same thing goes for this base library. So if we go to this base library here, you can see that this base library exports a bunch of functions. So clearly module.exports is not available in the browser. If you're in a similar scenario with some production code, you should of course look into something like Browserify, or maybe there's something more modern now. But now, I mean, we just do it. We can just hack it up. So I just simply said that in the global scope, I said that require is a function that returns an empty object, right? And module is an empty object. And module.exports is also, sorry, so let me also say, I mean, I said require here, but I said that the problem in this right hand was the module exports, but actually we have, so in Snake, for example, Snake actually does require, right? So Snake, the Snake implementation or the Snake game engine depends on the base functions, the functions in the base library, the base library helper functions. So here we make use of the word require. So the browser does not have the word require, and the browser does not have the word module nor module.exports. And when I say word, I mean, of course, I mean keyword. Sorry. So anyways, we just say that require is a function that returns an empty object. Module, on the other hand, is an empty object, and module.exports is a function that returns an empty object. Just to make them not fail, right? They're not doing anything useful. And then I'm relying on the fact that I know that both Snake, base and Snake and web are all defining their functions like this, right? Here's a function, here are a few other functions, here are a few other functions, and so forth. So if I just run this code in the browser, they will be exposed as global functions. So just a quick and hacky way of getting this to work. But anyways, that's the web, right? So what it does, so you can think of this as that web is actually the entry point, or web.js is the entry point, and then web.js needs to first require base and then require Snake, and this is why they're in this order. Or actually, I mean, to be perfectly frank, rather, web needs to require Snake, and Snake needs to require base. That's actually the more proper way of saying it. So that's web HTML. Let's now look at web.js, right? So what does this actually do? So we don't have a ton of lines here, right? Let me just scroll through this file. You can see here at Yeah, 53 here I'm saying, I added a comment here to say that this is the main portion, right? So let's actually start from this main portion. So what web.js does, so the JavaScript that will be run in the browser when we run the browser version of the snake game, right? First we do draw. So these are actually 2 lines, right? Sorry, I thought it was prettier to put them on a single line. So first we do draw, one initial draw, and then we say request animation frame. I don't actually really know what that is, but it's something like, well, the next time the browser will redraw using this function, please. Or something along those lines. So people who develop games tend to use these. So window.request animation frame, and then we pass the function step, or the function that's returned by invoking step with 0. And so importantly, usually people do this, right? They pass a function, but I'm actually invoking the function step because step, when invoked, will return a new function. And the reason for that is to avoid one global or another global. So step needs to keep track of how much time has passed since the last step, right? Because, so if I'm not mistaken, like, I mean, request animation frame might be called different times depending on the, I guess, frame rate or something like that of your browser, or the frame rate that you can manage to get on your browsers. Like, depending on the performance of your computer, the request animation frame will be, or rather, the function that we pass to request animation frame will be called with different intervals, different time intervals, depending on the performance of the computer that you're running it on. So in every call to step, we need to check the delta. We need to check the diff between the current time and the last time we rendered. And that's why I passed this first variable, because here I'm saying then that, or this first 0, because I'm saying that the time since the last redraw was 0. So we're saying let's instantly redraw. So here you can see then that here's the definition of the step method, right? So the step method, or the step function, I should say, sorry, it takes a t1, so a time step 1, or timestamp, I should say, a timestamp 1 and a timestamp 2. And then it says, okay, what's the difference between timestamp 2 and timestamp 1? And if that's greater than 100, and I don't really know, let's think about this. So I can't really remember, but I assume this is in milliseconds. So that would mean 100 milliseconds, right? So a tenth of a second. So every tenth of a second, we enter this portion, and all of the other times we enter this portion. And now you can see how this works, right? Because if we do enter this portion, if 100 milliseconds has passed since the last time we updated, or the last time we stepped, then what we want to do is we want to say this state, this global state variable, I'll get to this in a moment, equals the next state given the current state, right? This is kind of typical functional programming, right? Instead of doing mutation, we're just saying that we have this global state variable. Global, well, I mean, you shouldn't have a global state variable, but I mean, in this case, it happens to be global. But essentially, the point is containing your state into a single variable and then passing that state through a function that produces the next state, right, from that given state. So instead of saying, well, here's my state, here are the actions that I want to do, let's change all of the variables so that it matches the new state, because then some things are more difficult to reason about because we have mutation all over the place. Instead, we say, well, here's the old state, let me pass you that. And then if you compute what the next state would look like given that old state, well, then I know what to do with that, right? So that's what we're saying. State is this state variable, and we say next is a function from the snake engine, and when we pass state to that, it will compute the next state, and then we will set the state here, this mutable state here, to this new state, and then we will do draw. Right? And draw, I haven't even bothered about trying to make immutable in any kind of sense, because like the Canvas libraries, or the Canvas APIs of browsers are like there's tons of mutations that would be extremely painful. Maybe there's a way to do that. If you have an idea of how to do that, please do shoot something in the comment. That would be, or in the comment section, that would be very interesting to read about. Anyways, so that's for the if branch, or for the true case, right? For the false case, what happens? Well, in the false case, or in other words, when enough time hasn't passed, when 100 milliseconds hasn't passed since the last time we updated, then we simply do, my camera is in the way, I can see, but we simply do the same thing, or we say, or rather I should say, we don't compute the new state and we don't redraw, importantly, but we do request another animation frame, and to that we tack on, or we throw in a function that says step, again from T1. So notice the difference between this line and this line, right? In this line, we have T2, and in this line, we have T1. T2 and T1. And T2 here is because we want to have the new point, the current timestamp as the next timestamp that we want to compare against. So like as the next timestamp that we want to say has 100 milliseconds passed from this timestamp, right? That's what we want to do when we do redraw. But when we don't redraw, we want to compute from the old timestamp. We want to say, well, you started at timestamp 0 and now 50 has passed. 50 is not enough, so keep on waiting, but you should compare against 0 and not against 50, because if we keep updating this, if we keep changing this to T2 here, if I said T2 here, we would never redraw, right? Or maybe in the odd case if it's like it's super laggy or something like that, right? But assuming we have good frame rate, then we would essentially never call this, and then that'd be problematic. So this is why we're saying T1. And of course, I mean, maybe this wasn't clear, but what request animation frame does is that it passes a timestamp, and that is this T2 then. And I don't actually know. I mean, it's not like it's a date because we start from 0, but maybe it's something like the time since this browser session was initiated or something like this. I mean, since the page was rendered, I should maybe say. But anyways, I mean, I have no idea, so don't take my word for that. But that's the update method. But actually, let's go up to the top here, because I feel like what I didn't say is this, that the state variable that we talked about is defined here. So note this comment that says mutable state. So this is the state variable that contains the state of the game at all times. And it's global quotation marks, like it's shared across all of these functions in this file, and what you can do is that the functions, or actually the functions don't, there are two functions that change it, I should say, right? There's the step method that changes it, but there's also this key events thing, like there's this listener for key events, and that thing also changes the state, right? So actually let's look at that at once, right? Or wait, first let's begin here in the top. So we can say, okay, so we say let state is equal to the initial state. And where does this initial state function comes from? I mean, this is the problem of working with globals. It's very difficult to see where things are actually coming from since they're not actually scoped. I'm realizing now maybe I should have scoped them so that instead of making these functions all functions in this file, I could have put them inside an object, and that would give us a namespace here so that we could say snake.initialState, because that's kind of actually what we're looking at here. Like if you would use require, you would get that for free. But anyways, yeah, I should have fixed that, maybe. Yeah. But anyways, that's from the snake.js file. So snake.js file has a function called next here, right? And we'll talk about this when we get to the snake.js file. But suffice to say for now that the next function takes a state and computes the next state given that state. Oh, sorry, I was about to talk about initial state and not about next, but that's next, right? That's what next does. But if we look at initial state, that's just a function. It's I think it's called a unit function, like it's a constant in some sense. So it's a function that takes no arguments, so it's nullary, and it returns an object that is essentially a state representation, but it's the initial state. So the initial state is essentially always the same. So when you start a game, you need to start from the initial state. So yeah, that's the way we invoke this state variable. Now let's go back down here and let's now talk about these events. So we say window dot, so now my camera is really in the way, add event listener key down. So that's the first argument, and then the second argument is this function that takes a single argument, which is this variable named e, which is the event. And then we can extract the key variable or the key property from that event, and then we switch case over essentially that variable. And then we say, okay, well, we want to be able to control the snake using WASD, the keys, and HJKL. So here's WASD and here's HJKL, but then we also want to be able to use the arrow keys, right? So, and depending on which one of these we press, we want to compute a new state. We want to say that the new state is what the old state was, but plus, quotation marks, plus this new direction. So these are constants, north, west, south, east. These are constants that I've defined in this snake.js file, where we have north and south and east and west, right? And these are essentially just, I guess maybe you could think of them as vectors, I'm not really sure. But like they have an x direction and a y direction, or a velocity in these directions, right? So north means moving 0x, but -1y. That's the definition of north within the context of this game. But anyway, so we want to queue those in, and we need to pass the current state, because again, remember, the snake game has no clue of the current state that we have, right? It's actually, I should say this, it's pure, except for that the snake.js file has some randomness, right? So here we have one function that does some random stuff. And I mean, remember, randomness is impure because it relies on things such as system date and etc. So given the same input, you won't get the same output. But I mean, I was pragmatic here. I was just thinking like, there's no point trying to do something more complex here. In my mind, it makes sense for a function that computes a random position within a grid to be within the snake.js file and not elsewhere. But anyways, there are clearly solutions for that, but I'm just being pragmatic. But essentially, so then the snake enqueue method needs to be passed the current state. We need to pass the current state as we do here, right? And we need to do that because, as we do here, because again, it's almost pure, so it doesn't know what state we have. It doesn't keep track of its own state. And enqueue is also defined here in this snake method. And again, we'll get to this when we start to talk about the snake stuff. But essentially, as you can see here, it takes the current state and it takes a move. It asks whether the move is valid. And if the move is valid, it does this. If it's not, it does that, right? So if it's not valid, it just returns the same state. It does no changes. But if it is valid, then it says, well, okay, we want to merge. Yeah, we want to compute a new state that is the old state, plus that this moves property has changed to the old moves concatenated with an array containing only this new move. So this was an extremely complicated way of just saying append, but immutably append the last move to the list of moves. But we haven't even talked about the state tree, so we'll get to that in more detail. But that's enqueue, and this is sort of the basic game loop, right? Like if you think about this game, first from the main here, we draw one initial time, and that's sort of the first drawing. But then we say, well, start stepping from 0, and then we keep doing this step method. Okay, step and step and step and step and so forth. And whenever it's been 100 milliseconds since the last step, we compute the next state from the old state, and then we redraw, and then again we just keep on looping, quotation marks, keep on requesting animation frames. So that's sort of update and draw. But then there's also this other exogenous force that can enter, right? That like there are also key events. So like when the user types keys, we listen to this, and if you happen to type a key that's one of the arrow keys, then we need to compute a new state. So then we're also saying, well, you need to set the new state to the old state plus this new key that's being pressed. So I would say that's fairly clear. Again, like the benefits of mutation, or the benefits of avoiding immutation, is that whenever you want to change things, usually it's pretty easy to change things because you don't have to think about state. So for example, I'm not sure if you noticed, but when we played this game, well, sorry, of course, how could you have noticed? It's not actually visible. I didn't think about that. But the way the game worked from the beginning was that if I'm traveling in the direction west, as I'm doing now, and I press east, right? I'm traveling leftwards, but if I press the opposite direction, if I press east, right? Or conversely, if I'm traveling to the right and I press the left key, so if I press the inverse direction or the opposite direction of the direction I'm traveling in, I would instantly crash because it's like the snake is moving in this direction, right? And it's like it's immediately just going directly into its own tail, right? And some snake games actually did work this way and was extremely frustrating. And that's what I noticed here as well. Like when I was playing this, it just messed me up all the time because I kept on crashing when I wanted to try out the game. So I figured, okay, let's actually remove that functionality from my snake game. And that's when I added this valid move portion to enqueue. So previously enqueue used to only do this, right? It used to only just merge in whatever motion you added into the queue of motions or into the queue of moves. But now I said, well, actually, let's avoid this sort of inverse situation. So if you pass the inverse, so that's what valid move does. It checks whether it's the inverse. And if it's not the inverse, yes, then it's valid. But if not, if it is an inverse, then we will ignore it and we'll just pass the old state. So we'll not queue the move, right? So it's these kind of scenarios that we often find ourselves in when we use immutability. Like when we realize, okay, it would be cool if the game could do this, or actually this is a tricky thing. Let's not actually make it do this. Let's make it do that instead, right? And then we try it out, and it actually turns out to be fairly simple most of the time. But anyways, okay. So this is the web portion, right? We have the step function, we have the event listeners, we have, here in the main, let me just put that back on one line. We have this main that initiates it, and then we haven't talked about what draw actually does, right? So as you can see here, the comment says game loop draw, right? So this function draw, and it's also pretty simple. Like as you can see from the comments here, like I was contemplating separating this into multiple functions. But given the mutable nature of the canvas library and like given the fact that we probably won't reuse this code, I just figured whatever, let's actually just make this a long function that does all of these things like one by one. So what it does is that it clears the canvas, right? So ctx here is another global variable because what to do, right? So let's actually start from the top, right? So the first line says, okay, let's make a constant variable called canvas, and let's from the document get the canvas or let's get the thing that has the ID canvas. So if we look at the HTML thing, you can see that the canvas here actually has an ID of canvas, just to make it simple for myself, right? So I grab that canvas, and then we get the context for that so that we can draw. So in ctx is a context variable. Then we have these position helpers here. We'll talk about these in a moment. But what we do then is that we first clear this canvas by saying, okay, let's set the fill style to this like blackish color, I guess, and then we draw a rectangle over the whole width and the height. Then the next step is that we draw the snake, right? So then we say, let's set the fill style to something which is greenish, and then let's map over the snake. So this is where it sort of gets interesting, right? Because it's like the different graphics engines or the different GUIs or the different sort of interfaces can have completely different ways of interacting with this state, right? But so the state exposes .snake. It exposes actually lots of things like moves and apple and so forth and so forth. But we're just going to make use of snake and of apple. So what we do is just that we map a function over state.snake, and so snake is an array of positions. So it's an array of points being objects that have x and y coordinates. And of course, this is not an actual proper map because I don't care about the return results. So this is actually more like a for each that actually mutates the canvas. But map was a shorter word, so whatever. And in each of these iterations of the function, what we do is that we say, well, using this fill style, fill a rectangle in the context from this x position, this y position, over this width, and over this height. And now you can see why these x and y methods. And these x and y methods are just helpers for me so that I'm not duplicating the same math all over this place. So if you remember, what we did was that we drew rectangles, right? So notice how the snake, so every point in the snake or every piece of the snake, or just think of the apples, for example, take up sort of one quotation marks pixel, and pixel meaning like traversable pixel in this grid. Maybe I should say tile, actually, like it covers one tile. And so what we do then here is that we compute the position of these tiles. So x1 here will return the width of one tile, and y1 here will return the width of one tile. And what happens when we do this, y of some position, is that if the y coordinate is 0, then it'll turn to 0, right? Because if we look at the implementation of y here, we say take the canvas height and divide it by the number of rows that we have in the state. So like if the sorry, I forgot to say that we have the r here as well, right? So if r is 0, r being the y coordinate, right? So let's say that the y coordinate is 0, and then we multiply that with the height of the canvas, and let's say that the height of the canvas is 100, and then we divide that by, let's say, 20, which is the number of rows, let's say, so the number of tiles in the y direction. Now this is not necessarily correct in regards to this particular scenario, but just hypothetically it makes sense. Then you can see that we get 0, right? Because that's a 0th position, like that's the pixel that we actually want to draw from. But if we take 1, we get 5. If we take 2, we get 10, and so forth. And if we take 20, we get 100, because like that's the last pixel. And actually 20 doesn't exist if we have 20. It's 19 would be the last one, because its height will also be 5, and then 5 will take it up to 100. But anyway, so those are just two helpers in order to not have to duplicate that. As you can see, we use these x and y things here as well. So that's the way we draw the snake. And then we do that for the apple as well. So we say, okay, here we don't have to actually iterate. We just say fill rect at this x position, at this y position, using this width and this height, right? And the width and the height is the same because the apple is as large as a tile, just as all of the pieces of the snake is as large as a tile. But the position is based on the x position of the apple, right? So the x position and the y position. So we're saying compute the y position from this coordinate, which is defined by state.apple.y. And then finally, we draw the crash. So let's just think about, so let's just look at that, right? Like if I crash into my own tail, notice how the screen flashes quickly red, right? Or quickly flashes in red. There you go, right? It quickly flashes in red. And how we know that that has happened is that I decided that, well, if we don't have a snake in the game field, that means that either the game has just started or there was a crash. So actually, if we just refresh the page, you can see that it blinks red. And maybe this is an unwanted feature and we should try to solve this, but I just figured, whatever, let's just not think about that now. So if there is no snake, right? So essentially then we're saying that if state.snake.length is equal to 0, so if we don't have a snake, then we should essentially draw this red rectangle over the whole screen, right? So that's the way we're indicating a crash. And that's the whole drawing thing. And I mean, a moment to pause and reflect, right? Like the point here is that this is all graphics, right? Like assuming that we can use this state structure for all of the graphics engines, assuming that state tree gives enough information, this can be completely focused on just the visuals, right? And is not sort of intermingled with all of the business logic. So if we say, actually, let's change the color of the snake, it's trivial to find the place where we can change the color of the snake. Or let's make the apples round. It's trivial to find the place where we make the apples round instead. And we don't have to worry about accidentally messing up some of the other core business logic because that's in a completely different place. So we have to be really silly in order to mess that up. So anyways, that's the draw. That's the draw function. And I think actually we've covered all of the stuff here then, right? Like first we just grab out the canvas, we set up this mutable state that's based on the initial state. We construct these two position helpers that will make us position things in this grid or a visual grid in the browser. And then we construct this draw function that will take the mutable state or based on the mutable state draw a bunch of stuff on the canvas. And then we have this game loop that whenever it's called checks whether it has passed enough time in order to progress to the next state and redraw, or whether it should just keep on ticking. And then we have these listeners that listen for events or listen for keystrokes and produce new states based on these keystrokes, where the new states contain the new keystrokes or contain the directions that we want to move in. And then finally we have this main that sort of just initiates and starts the whole thing up. And of course, I mean, we didn't actually need this first draw here in the end, right? Like the only difference if we have that, or if we remove that, you can see that there's a quick flash of 100 milliseconds where we don't have a board. That's essentially the only difference, and that's why I added that, because then immediately we should get the board. Actually, now that I think about it, it's almost hardly visible. I mean, like you can see, I mean, loading the page probably takes quite some time anyway. So yeah, I mean, you might want to remove that. Okay, but that's the web portion. Let's now actually look at the Snake core library. I think it's probably easier to start with that and then look at the command line implementation. So let's go to snake.js. So again, this is we've glanced into this file a tiny bit, but not too much. So I think actually there's too much code here, right? So let's start from the top. Let's just scroll through quickly first to get an idea, right? Like we have about 61 lines of code, and if you have ways of making this again more elegant and more concise, not concise as in code golf, as in just for the sake of conciseness, but as in elegance, then please do shoot something in the comments. That would be massively interesting. But what we start by doing is just requiring this base library that we've defined, again as we've talked about, with some helper methods. I'm not sure if we actually ever looked at that, but here's the base library, right? Yeah, we did quickly look at that, but we just define a few functions, such as, for example, map, and as constant, and as identity, and all of that stuff. But let's forget about that for now, right? But we load the functions from the base library, and then we do this. And this is kind of just me hacking again, so I apologize for that. But what I wanted to do is, so base, for example, exposes the function map, right? So you have base.map. But whenever I don't want to have to say base.map. I just want to be able to simply say map and refer to base.map, because they are helper functions. So, I mean, in some sense, you could argue that some of the functions defined in base here are functions that should be defined in JavaScript, if JavaScript was actually aiming to be a functional language. Like, so functions such as map or reduce are defined in the prelude of Haskell. So they're defined in the base library of Haskell. Reduce is actually called fold in Haskell. And not just that, I mean, tons of other methods, such as identity and constant and lots of other things. Some of them are not, like prop, for example, like because Haskell is a statically typed language and JavaScript is dynamically typed language. So if we look at the base library here, for example, I defined the helper method prop, which essentially takes a key and then takes an object and extracts the value under that key from that object. And that's trickier to define in a statically typed language. Actually, now that I'm thinking about it, actually it's completely definable in a statically typed language. It's just probably not as useful, right? Because you're probably using static typing because it gives you benefits. And when you're starting to use this sort of key value pair syntax, this dictionary syntax, then you are exposing yourself to runtime errors because you might end up in situations where the key doesn't exist. But anyways, that's tangential. What I wanted to say is just that in JavaScript, because of the dynamic nature of JavaScript, some of the functions that we might want to put in the base library, quotation marks, make sense to put in the base library, but might not be functions that we want to put in the base library in other languages. But anyways, this is total sidetrack. That's why I'm doing this, right? Just to expose all of those functions so I can say k and id and map and so forth, and not have to say base.map and so forth. So that's that. Okay, let's move on. Then we have these constants, right? These constants we've already talked about. We need some way of talking about the different directions. And maybe you could argue that these should be functions that, or again, like nullary functions that take no arguments and return this. But anyways, I just define them as constants. Then we have this point operation. And actually, I was thinking about this a while. Like, this is not excellent because if you could check for deep object equality, right? Like, I think in many of the JavaScript libraries you can do that, and many of the testing libraries you can do. So actually, like, object deep equals or deep equality of two objects is actually a very useful thing to have in a language. So actually, I mean, the implementation of point equals should essentially just, like if you pass point 1 and you pass point 2, then the implementation should essentially be point 1 equals point 2. If equality in JavaScript was based on the deep structure of an object and not the reference to that thing in memory, or the pointer to that thing in memory. But anyways, I mean, and even if it didn't look like this, it should perhaps be the deep equality between P1 and P2, and maybe if we do that in a curried fashion, it would look like this, right? And actually, if we have that, then point equals is essentially equal to deep equals, if you think about that, because if I put both of these at the same time, you can see, I mean, what we do is simply that we take one x here, one y here, we pass the x here, and we pass the y here. So we're just applying that function. So then it's the same thing. Like, we don't even have to take any arguments. We can make it point free. And that's the reason I'm complaining about this. Like, point equality is nothing special. Like, I want to say that the x point equals the x point and the y point equals the y point of the two things. Or not the point. I mean, the x property of point 1 equals the x property of point 2, and the y property of point 1 equals the y property of point 2. Like, that's a check I want to make. But that's just a check of equality. So that's why I'm saying, like, that's a bit silly and that was disappointing. But I figured it was just overkill to implement deep equality, a function of deep equality in the base library. But at least now you know. Anyways, let's move on. So then we have a bunch of Boolean methods, right? So what I mean here is, I mean a bunch of functions that take some particular or potential arguments, but also the current state. And then given the current state, answers questions. So the questions that we want to have answered is whether the snake will eat upon the next update, given the current state, and whether the snake will crash given the current state in the next update. So if we have this current state and we have a list of moves, so we have a list of left, right, up, down, etc. Given the next move and the current state, will the snake crash? That's the things that we're asking here. And then this thing is, of course, as we talked about before, whether a particular move is valid. But that's before we enter the move into the state. So, I mean, maybe we could have done it in a way. We could have just blindly added moves into the state and then have a function that computes a clean state without any invalid consecutive move combinations, or without any sort of inverses in the list of moves. But I chose to do it this way. Maybe the other way would have been more elegant. But so you pass a move first, and then you pass a state, and then it says yes if this move is okay given this state. So if it's okay to add this move to this state. And the way we do this is just that we say, okay, well, so let's think about this. We do logical OR between this thing and between this thing, right? So let's put these like this, just temporarily so that we can think about it, right? So we're doing the same thing twice. We're saying either something holds for the x-axis or something holds for the y-axis or for the y direction. And if either of these hold, then it's a valid move. And what needs to hold is that the x velocity of the move, of the last stacked move, of the next move that we have, when we add that to the new move that we want to add, that needs to be different from 0. So what we're saying is that if we are moving in x minus 1, then if we add 1 to that, then that would give 0, because if we're moving in this direction and then we add 1, so 1 would be this direction. That would be the polar opposite of that thing, or of that direction. Similarly, if we're moving 1 and we add negative 1, we get 0, because if we're moving in this direction and we add this direction, then these cancel out and we get 0. Right? And that's the scenario that we don't want, where we're crashing into our own head. But we're saying that either the x-axis needs to be different or the y needs to be different. I mean, since you can't move diagonally, yeah, this is in some sense probably overly complicated, because clearly if the y-axis has a value, then x will be 0, and if the x-axis has a value, or if the x direction has a value, then the y will be 0. So there's probably a more simple implementation that you could look for. So let's go backwards by putting this back on one line, and then let's look at the next stuff. Actually, before we go any further, let's look at the state, right? So initial state, let's go here. I mean, we said previously that there's a function called initial state that returns the initial state that all of the other states are sort of built from. So in the initial state, we have just a few things, right? We have some number of columns and some number of rows, and these are just in order to, I mean, maybe it's not the best place to store these because they won't change, or they shouldn't change over the course of the game, but maybe if you would think in terms of levels, then maybe this could actually change, but who knows. But then we have a list of moves, and in the initial state we start with east in the list of moves. As you can see, right, like when we refresh the game, we always start from the same position here, and we always start by moving east. And that's because the default move is east, and we can't see here because the default snake is empty, but what happens after a crash is what causes the snake to start at 2-2, but we'll see that later. And then we start with the default apple actually at 16-2, so maybe that should be a random position, but for some reason I chose to put it there. So again, you can see that the apple always starts here, so we'll always automatically catch the first apple, right, by just leaving the snake to do its thing. So that's the initial state. But let's now jump back. Now you know sort of what that contains. And of course, the snake thing, right? Like we were saying, the snake is an array, and it is an array of positions or points, right? So things that look like this, right? That have an x coordinate and that have a y coordinate. And this is why we're saying point equal, or this is why I said point, because we call these things that have .x and .y, we call these points. So yeah, actually, so let me jump down. I think it's actually easier just to follow along from down here instead of going line by line, because the order wasn't superb. So let's actually just look at the next method here instead. So when we looked at the web implementation, if we go to web.js here, you can see we talked about how we call the next function here, right? When we step the game, we say the new state is equal to the old state ran through the next function. And the question is, what does the next function do? Well, the next function is, I make use of this library method called spec, which the library Ramda, I think they call it apply spec or something like that, but I just called it spec. So you can see spec is a fairly interesting method. It has this slightly tricky implementation where it takes an object, and then it takes some value, and then it grabs the keys out of this object and maps over the keys, constructs a new object from that key, and runs the function that hides under that key, applies that function to this x that we passed, to this value that we passed, and then it reduces over merge. So it simply merges all of these different objects that it produced into a single object. And that's a pretty complicated way of saying that essentially what we do here. If I retype this implementation, we could retype it as that. Let's think about it. Next is a function that takes a state and returns a new object, where the new object, if I had a spread syntax, I could say is the old state, right? Plus, or actually, let's not use the spread syntax. Let's be explicit. So takes some state and returns a new object where rows is equal to state.rows, calls is equal to state.calls. moves is equal to next moves while being past the state, and snake is next snake being past the state, and apple is next apple being past the state. So that's essentially what we're doing. And actually, I mean, if we would express this in function syntax as well, these first two, just to make it clear, really why we can use spec in this lower implementation, is because this is essentially then just using the prop method that we talked about before. So if I say prop here, pass row, like this, right? I pass these props as a string, and then we pass the state as the second argument. And sorry, I'm using curried, or functions that allow partial applications, so we actually need to invoke the function like this. So that would be the same thing. And now if you look at that, right, if you look at that implementation, you can say, oh, okay, well actually, next is a function that takes some state, produces a new object where the state needs to be passed to all of the functions, or rather I should say so next is a function that takes some state and produces a new object where this new object contains a bunch of keys, and to determine the values under all of these keys we need to execute a few functions. But these functions, they are not nullary. We need to pass them some arguments, and the argument that we need to pass is essentially the state. Like if you line this up, you can see all of them are past the state. So essentially what we did is just that we sort of made it point free. We remove this portion. Notice how we do this. We remove this, boop, and then we say, okay, all of these need to be past state, okay? But that's why we have the spec method. So then we say spec, and then we pass state here, okay? That's also the same thing. But then we're back into the scenario that we looked at before, where it's like, well, actually, next is now a function that invokes this function spec by just passing the x that we pass it, right? Like next is a function that takes an x and runs another function through that x or over that x, and then we don't even need to specify the x. We can just remove the state here, like we remove the explicit call, but then we remove this explicit variable here, and then we just say next is the running of spec over these functions, and then we pass it some state. So, I mean, I would argue that this is more clear, but I'm totally empathetic to if you have a different opinion. Like, as soon as you start to learn a few of these really common functional programming, I wouldn't say patterns, but like functions, essentially, these common functions that we tend to use all the time, like constant and id and map and reduce and pipe and compose. And I would argue for dynamic languages, this method is like super common, or this function spec or apply spec is super common. So when you start to recognize these, I actually think this becomes the easier version to read. But there's a whole discussion about whether point free is sensible or not. I can shoot some links in the description if you're interested in that. But anyways, let's move on. So that's the next method. And we've already talked about enqueue. What enqueue does is essentially that you pass it a state and you pass it a move, and if the move is valid, then you merge the move into the list of current moves that you have stacked up, right? So the reason we're stacking them up, by the way, is that if you think about it, what we can do, let me collect a few of these just to get a tail. But what we can do is that we can stack moves like this. If I just mash the buttons, now I have a tail, now I can do this. Okay, so if I just mash the buttons and then I let go, let's see if this works. Whoa, let's not crash. I just mash the buttons and I let go. You can see that we've stacked a few moves. And the reason we do that is because if you've ever played the game of Snake, you can see, like literally in this scenario, right? Like now I just want to go right down, for example, like immediately right and then immediately down. And then I can just queue down after right. So I just press right down and then I've queued it. So like if we didn't do something like this, maybe we wouldn't be able to get both of them in. But actually, now that I think about it, that would probably work still. I don't know. Maybe you have some opinion about that. I mean, what wouldn't work is this sort of stacking, but then again, this stacking isn't necessarily super useful, I assume. But anyways, let's get back to the code. That was the original intention of why I did it as a list. So yeah, that's enqueue. So we've talked about enqueue, we've talked about next, we've talked about initial state, and I guess what we should do now is just talk about, well, first let's talk about these. So the next state is computed from the old state, right? And rows, when we do prop rows and prop calls, as we looked at in the other implementation, that just equates to the same value. Like we just say, this value is whatever the old value was. But however, next moves, let's actually look at next moves, right? So let's search for const next moves, right? And what this does is that it says, okay, it takes some state, and remember, so what it does, the intention is that it takes the whole state, but the intention is that it should produce only the list of moves, right? So it takes the whole and it produces the part. So we take the state and then we say, okay, state.moves.length is greater than 1. So we say, if we have more moves than 1, then we should drop the first move, right? So drop first is a function that I've defined here in the base. Drop first, which is, I mean, it's trivial. We just call a slice on an array, slice and then pass 1. But I just did this to make it more readable, right? Because now we can actually like very easily see what it does. So we say drop the first from state moves, or if the length of the moves list is not greater than 0, right? So if we have only a single move left, then it will simply be state.moves. So what this means is that if we have more than one move, we will drop the first move because we've used it. Like in the next state, we won't have we won't have the first move left because we've now used it. But if we have only a single move, then we shouldn't do that because we want to keep repeating that move, right? That's how we're achieving this effect where it just keeps moving right. I mean, I'm not touching anything, but it just keeps moving to the right. So that's because we keep that in. And of course, let me just quickly mention again that you can, using functional programming, you can make a lot of things point free, point 1, and point 2. I've also kind of mixed this sort of object-oriented dot syntax with this function syntax where you truly have a function and then pass the data. And I'm a bit disappointed about myself for doing that, but anyways, I mean, I just figured let's stay pragmatic. But probably like here we should do something like this, like length of state.moves, because this dot syntax is fine because this is purely data, but then length is a function on that. But this is a sort of give and take. I mean, I don't think we're going to be able to get away from this anytime soon in JavaScript, because like maybe my terminology is a bit shaky here, but if you've tried Haskell, for example, like you have ad hoc polymorphism and you have parametric polymorphism, and ad hoc polymorphism is kind of like polymorphism in object-oriented programming. And so the thing in Haskell is that you can actually define a length function that takes some data and then does different things depending on the type of that data. That's a bit tricky in a language such as JavaScript, because we don't have ad hoc polymorphism in that way. The way we achieve ad hoc polymorphism is through object-oriented polymorphism, is by saying that length is a function that exists on an object. And in a dynamically typed language such as JavaScript, we say, well, everything is a duck type, right? Like if it quacks, it's a duck. So everything that responds to length is lengthable, but which implementation of length you get depends on which object you call the method length on. So I mean, it's a give and take. Like we probably have to mix these two types of syntax before we have facilities for ad hoc polymorphism that looks a bit more like something like Haskell in JavaScript, which probably we maybe won't, because maybe I'm not realizing how difficult that would be to implement in a dynamic language. But anyways, now we're way out of the zone, so let's get back into this game. But I just wanted to mention that I'm completely aware that it's not superb. Anyways, how do we compute the next position of the apple? Well, if this is when we get to this will eat that we talked about, right? Like if the snake will eat the apple given the current state, then we need to spawn a new position, and that's when we're using this R&D pos that we talked about. That is the function in this snake library that is impure. Or actually, I mean, then next apple becomes impure because it's making use of an impure function, but whatever. So if the snake, given the current state, will eat the apple, then we need to spawn a new position for the apple based on the current state. If it's not, right? If the snake is not going to eat the apple, then the apple will maintain its position. The new position for the apple will be the same. So let's actually, for the fun of it, I mean, let's actually do the same thing in both of these cases, right? Like we have the cases where it will eat and we have the case where it won't won't eat. So let's change the won't eat case to also spawning a new apple at a random position. And then if we refresh this and run this again, you can see that it's absolute and total madness, right? Because now we have the apple is sort of respawning at new locations regardless of whether we're eating the apple or not. So actually, I mean, I don't know what the probabilities here, but it's probably, I have no idea whether it's higher or lower, but like it's a very tricky game to play. So this is surely not what we want. And then also for the fun of it, let's try the other thing. Like let's say instead of when we eat an apple, that's spawning it at a random position, let's just spawn it at the same position. Let's say that the new position of the apple is the same as the old position of the apple, regardless of whether we ate it or not. Then we can see that what happens is that we don't spawn a new apple, right? The game works fine, but we can just like hands off and then just leave it like this because we're just going to eat all the apples until we crash. Actually, it's probably still tricky again because the snake will take up all the screen and then it's going to be tricky to eat the apple. But anyways, I mean, clearly what we want is a random position. So what we want is this, like we spawn a new position when we eat the apple. And again, there's like some of these things that are very easy to think about when you have immutability. Like I would imagine that going back and forth between these two changes would be more difficult if you had, it would potentially be more difficult if you had mutable state, depending on how you had structured your code, clearly. Next thing, let's move to next head, right? So next head, well, let's think about it this way. We have next snake and we have next head. So maybe these should be in the other direction, right? So, and I think next snake was called in the next method here, right? So yeah, so we're saying snake is equal to next snake. So if we go back to next snake here, and next snake makes use of next head. So let's actually talk about next snake first. So let's first think about the snake, right? Like look at this. Like let's actually grab one more apple here. So now we're a snake of 3 dots, right? If you look at it, now we're 4. But so the snake is a list of positions, and now it's a list with 4 elements that each have positions. And I think, if I'm not mistaken, yeah, we'll have to see. Either the first element or the last element in the list is the head of the snake. So what we do is that we just, when we need to move the snake, we remove one element in the end, and then we add one element in the beginning. And when we eat, right, think about it, look at what happens when we eat, then the snake is prolonged. So what happens is that we add one in the front, but we don't remove one in the end. Or I shouldn't say we add one in the front. What I mean is we do compute the next position of the head, but we don't remove one from the tail, right? So we have the snake here, and then we're saying, okay, if you're not eating, we should just take the snake and move it here. But if you're eating, then we should take the head and move it here, but the tail should be fixed. We should not remove anything from the end, because it's this removing that gives the appearance of it moving, right? Because it's actually that we remove this thing. Maybe it's easier maybe if we just think about one dot, right? Like if you have one dot, like one snake head, then what happens when we're not eating is that we're just saying, okay, remove this, boop, and make another one here. And that gives the appearance of moving, right? Choop, and then choop, and so forth. But if we're eating, we're saying create the new one, right? You have one here, create the new one, choop, but don't remove this one, right? So we give the appearance of prolongation and not of extension and not of moving. Of course, of moving as well. But anyways, so that's the way that we structured that. By the way, I mean, I tried this in multiple different approaches. I also it's an interesting game because you can also approach it by building up a grid and then sort of making operations on that grid. So like you have a 2x2 array, like a matrix. But anyways, maybe if you try out the solution along those lines, maybe again shoot something in the comments that would be interesting to look at. So to compute the next snake, what do we do? Well, what we do is that we have 2 ifs. We have 2 nested ifs. We say, okay, if the snake will crash, right? Given the current state, given the current direction, given the current world, if in the next state that we are now computing, will the snake crash or not? Like, if it will crash, then the next snake is going to be an empty array. Then we're going back to this sort of initial state thing. We're saying, let's go back, the snake is an empty array. However, if the snake won't crash, we do any of these things. And if it won't crash, we're asking this. Well, is it so that the snake is eating? Because if it's eating, then what we want to do is just that we want to add the next head. We want to compute the position of the next head, like we did here with the hands, right? Like we have the snake here, and we want to add the snake here, or we want to move it here, right? And if it's eating, we just want to compute this new position, and then we want to concat that into the current, or with the current snake. However, if it's not eating, then we need to move it, or we need to give the appearance of moving. That means we can't just compute the new position, but we also need to drop the last position. So we need to remove something from the end. And let's just think about whether it's in the head or not. So what we're doing is that we're saying that the head is an array, and then we concat that with the old snake. Yeah, so what we're doing is that we're adding into the beginning, right? So we're not, it's not that we're pushing in positions into the end of the snake, but it's more like we're adding at index 0, and then we're shifting all of the other ones backwards. So I haven't at all thought about performance and efficiency, but I mean, clearly there are probably multiple ways you could improve this code. But so that's what happens when when the snake is eating. We are adding a new head, but we're not removing the tail. And if it's not eating, we're adding a new head, and we are removing the tail. So actually, I mean, if we remove this drop last, just to try this out, right? Then we're saying it's going to get longer all the time. So if we run this now, you can see just like it's never ending. Like, it doesn't matter if we eat or not, the snake is just growing and growing. And yeah, that was tricky for me to handle. But as you can see, right, like the snake just keeps on growing and growing and growing. Again, like a trivial thing to change. But we go back to actually dropping the last. And of course, if we did drop last here as well, just to be exhaustive, let's try that as well. That would mean that even if we are collecting apples, nothing happens. Like, the snake isn't actually prolonged. So of course, what we want is that, like this. Okay, that's the next snake. But then, okay, as we were saying, next snake makes use of next head. So the question is, how do we compute the next position? And that's actually pretty interesting, right? So let's look at next head. So again, next head, the structure is that it takes a state and it produces a single position, right? So think about it. I mean, next snake takes a state and produces a list of snake positions. Next head takes the full state and produces a single position that represents the head of the snake. And what it does is that it too has to ask an if question. And the if question that it asks is that, do we currently have a snake or not, right? Like, if the length is 0, like if you look here, right, as we talked about in next snake, of course, when we crash, we completely wipe out the snake so that we don't have a snake. So when we compute the next head, it might be that we're trying to compute the next head from no snake at all. So this is why we're asking, is the length 0? Because if it is 0, then this we want to, is like the default start position. Maybe I should have had that as a comment or something like that. Actually, if you look at it, if we refresh here, you can see that this supposedly is 2, 2. Actually, let's think about it. That means so x3 and y3 if you start from 1. So this is why, I mean, maybe one would assume that it's here, but actually this is 1, 1 because this is 0, 0. So here it's 0, 0, 1, 1, and then 2, 2. So yeah, we start at 2, 2 all the time. And that's essentially because when the length of the snake is 0, then we spawn at 2, 2. And again, I mean, we could do R&D, let's say R&D pause given the state. Yeah, that should work as well. Then we are starting at random positions. We're always starting going east, but now we're spawning it at random positions. We're spawning the snake at random positions. But I figured this makes sense. I mean, it's kind of nice to start from 2, 2. And then also it's obvious that you've crashed. So that's what happens if the snake is 0, like if it's the initial case. But if we do have a snake, like if the length of the snake is currently longer than 0, what do? Well, this I found pretty cool. We create a new position that has an X and then that has a Y, of course. And what we do is that we take I mean, think about how these two look very much the same, right? Like X and Y is essentially the same thing. But what we do is that we say the X position is the current X position of the snake, of the current head of the snake, right? What's in the 0th position, plus the X of this move that we've stacked, the next move that we want to grab. So the move that is pending, the move that we're supposed to execute now. And remember, like, the moves that we can have are any of these: north, south, east, west. So if we have east stacked, right, as in the default case, then X will be 1. So what we're saying here is that we're saying state dot is snake. So we're taking the snake position, and supposedly if we start at 2, as we've defined as the sort of default start position here. So if we start at 2 and then we say plus and we add 1 because east is 1, so the default direction is 1, then we get 3, right? Because the current head is at 2, 2, or if we only think about the X position, the current head is at at x2. And then if we add 1, we end up in x3, right? And that's actually the next head. Now, the question then, and of course, maybe what we should mention is that this, of course, works for negative as well. So if the position is 2 and you add -1, then you get 1 because you're moving in the other direction. And the reason then that we have this mod thing is that we're making use of the modulus operator. So actually, I mean, in the best of worlds, I wouldn't have had to write that. I should have been able to write something like, let's think about this. So the same calculation mod state.calls. That's the way I wanted to use it, like we want to use the mod operator. But apparently the modulus operator in JavaScript behaves differently than I had expected in regards to negative numbers. But think about it, the reason we use modulus here is that because we want to have this wrapping effect, right? Like, notice how when we go out of the right end of the screen, like it's a torus, right? We go out on the right end of the screen and we show up on the left end. And similarly, if we go out on the left end, we show up on the right end. And that modulus operator is actually everything that's needed to implement that. Because what we're saying is that if the grid, let's say that the grid is 12, right? Like, let's think of a clock. So if, I'm not sure if I can do mod here actually. So if I do 10, yeah, I can't. Okay, so let's do it in Google. So if we do 10 modulo 12, for example, we get 10 because, so let me be more clear. So if 12 is the width of the grid, and we're talking about the x position, let's say. So the number of columns that we have to work with is 12. And that means that 0 is an okay position, 11 is an okay position, 12 is not an okay position. So if we do 0, 12, modulo 12, that means that it's the 0th position. So what I mean is that 12 is the size of the grid, and 0 is the position that we want to position the next head in if we don't think about this wrapping around, right? Like, then you could say position 316, right? Like, even if you have a grid of 12. Actually, I mean, we could do that. That's the point of modulo. So if we do 316 modulo 12, that means that if you try to move to position 316, you should actually be at position 4, because you've wrapped around, you've looped around multiple times. But if we just think about the edge cases, right? Like 0 yields 0. So that means the 0th position. So that means we're not changing 0. And if you do 12, you also get 0, because 12 modulo 12, like 12 divided by 12, gives a remainder of 0. So that also puts you back in position 0, which makes sense because we're saying it's 0 indexed, right? So because we have the 0 index, the max index is 11. So when we try to go to 12, we should wrap around back to 0. So maybe I'm not making a superb job of explaining this, but every number then between 0 and 11 inclusive will be the number that we pass. So if we pass 2, we get 2. If we pass 3, we get 3. If we pass 4, we get 4, and so forth. But if we pass higher numbers, which happens when we are at position 11 and we pass 1, right? So, or we add 1, right? So this is more like the scenario that we have. We are at position 11, we pass 1, and then we do modulo 12 of that. So that gives us 12 that we do modulo 12 on. And that gives us 0. That makes us wrap around back. And let's jump into Node quickly and look at this. So actually, I should have done this in Node from the beginning. So 10 modulo 12 gives us 10, right? But 12 modulo 12 gives us 0, which wraps us around back. Similarly, 13 then gives us 1, but this is a case where that we're never seeing. However, what I would want is that -1 should also wrap. So -1 should put us in the other end of the 12, and that's the way I was expecting that modulo was behaving. So let's see, can we require the base library from here? So let's try to require base. Oh, sorry, base equals require. Oh, sorry, because now I declared it twice, but messed up. So let's restart, jump back into Node. So let's require the base library. Wow, sorry, I'm such a confused person. So let's jump into Node and let's say const base is equal to require from the current directory the file called base. Let's just be specific and say .js. Right, and that works. Then we have the base library, and base, the base library that we've defined in this project. And base has the function mod, right? So this mod, however, works differently. It works the same if you pass 10 and 12 again. Then you get, no, sorry, it's the, okay, sorry, for other reasons I did it in the other order. So here I pass, so this, if I pass it this way, I mean 10 modulo 12. Then we get 10. And if I pass 12, we wrap around to 0, similarly for 13, but again, we never end up in that scenario. But now if I pass -1, we wrap around in the other direction and end up at 11, and modulo 2, and so forth. So yeah, and that's a different implementation of modulo, and I think I left a comment here. Yeah, I left a comment here to a link that you can check out if you're interested in the source. I think that came from a Stack Overflow post or something like that. So anyways, that was one of these moments where you go like, excellent. Like it's awesome when math can make problems that seem a bit tricky to solve in programming, but math makes them trivial. Those are the good days, right? But anyways, so that's why we do modulo here. So what we're saying is that this is the raw, quotation marks, the raw new position, and then we say take that position and do modulo of the size of the rows or the calls, depending on which one we're working with, so that we wrap around. But yeah, that's next head, and so next snake is based on that next head essentially. And yeah, the randomness here we've talked about, the initial state we've talked about, next we've talked about, and Q we've talked about. Oh my god, have we actually talked about everything now? So yeah, I think we've talked about everything, and that sort of covers it in getting to the point where the snake game is operating something like this, because we also looked at the web HTML and JS file, and of course, I also have this web.css file with just some basic styling in order to make this look a bit prettier. If we remove, I'm not even sure, like if I remove this stuff, it looks like this, right? I've actually zoomed in. So this is what we actually draw on the canvas, but this is just some basic styling that I added in order to make it look like this. But yeah, that's it. Before we wrap this up, let's actually also look at the CLI. So the command line interface, so I'm opening up CLI.js, right? And let me just map a keystroke here in Vim to run node on CLI.js, or to run CLI.js through node. So if I just hit that, we're running this. And again, you can see this works fine. And actually, this is a pretty short implementation as well. So the game loop is a bit different here. We still do this sort of showing and stepping, but what I do is I set an interval. Yeah, so what we do is we make use of set interval, right? Which is this function in JavaScript that calls a function with a regular interval. And it's also expressed in milliseconds, but here actually I run it every 80 milliseconds. So yeah, for some odd reason, I chose a different interval for the terminal application. Maybe we should change this to 100 in order to sort of make it have the same speed, but never mind. That we can trivially change. But essentially what this set interval does is that it does these two things, right? We pass a function to set interval that first calls step and then calls show. And actually, now that I think about it, what we could have done is we could have said pipe step and then show, like so, over 80. And that should be the same. That should be the same thing, right? And actually that didn't work, and I think it has something to do with like the console log here or something like that, so like the context disappears. But never mind, let's not think about that now. And either way, piping here is not necessarily a sensible thing to do, because step and show are mutating functions, or there are functions that compose and pipe we usually use when we actually want to pipe or compose functions, like because we're actually passing data through. Now we're just saying do this thing and then do that thing, so like never mind. But anyway, so set interval, what it does is that it calls step and then it calls show, and it does that every 80 milliseconds. And what show does, let's start with the show, right? So both of these, both show and step, are functions that don't take any arguments. And show, what it does is that it console logs this strange character, which works as a clearing, right? Like if you think about it, actually if I remove this, I think that would be the most simple way of describing this. Like if we remove this and then redraw, you can see that the game works, right? But if I scroll out, you can see we have multiple versions of the game, where the lower one, this one here in the bottom, This one is the active one because that's the freshest one. The other ones are histories, and actually we are printing and printing and printing, and so it's not like it looks static, but it's not actually static. I mean, it's like a moving, like these old animated movies, like where you draw, where you pull past a strip of multiple images, and that's actually exactly what happens now. Like this is a strip of multiple images. Anyway, sorry, let's stop thinking about that now. It's pretty interesting. But if we add that character, we keep clearing the screen all the time, so that we're just it's like clearing the canvas. So that's the first part of show, like we clear. And then what we do is that we have these functions on the object matrix, right? So here you can see we have a comment that says matrix operations, and then following that there's a constant called matrix, which is sort of a module with a bunch of functions that operates on matrices. And actually, I mean, I use the word matrix here indicatively, like it's not actually truly a matrix, but what we have is that we have an array of an array, like we have a two-dimensional array where I think first I do rows and then I do columns, or maybe the other way around. So anyway, the things under the matrix module are then things that operate on this type of structure. So what we do is essentially then that we say, okay, matrix.toString of matrix.fromState given the current state. So here we probably could actually use pipe in a sensible manner. So what we're doing is that we're saying, pipe matrix from state and then matrix to string, and we're piping that through the state. So this is probably the reason why I didn't do this, because the line turned out to be longer. Like if you compare the two lines, this is actually longer, but that should work fine as well. And like if we run that, that doesn't work fine. Oh, sorry, my bad. This is probably why the other thing didn't work as well. We're not using array syntax. I should pipe like that. Yeah, sorry, so that's probably why the other thing didn't work as well. Maybe didn't have anything to do with the console log. But anyways, so yeah, we could use a pipe there instead. But as just said, I mean, even if I remove that sort of array here, you can see that this line is longer, and I just figured, never mind, let's just do this. But anyways, both of these things are equivalent. But yeah, maybe this one is more clear, so maybe let's keep that one. I guess I didn't because of the length of the lines. Like you can see, we're at 88. We're at column 88. But anyways, let's keep it like that for now. So that's show. So what it does is essentially it clears the screen. It says construct a matrix from the current state. Remember, the state is the same kind of state that we used in the web GUI, right? Like that's what we're saying. Like we use the same state tree, but we do different things based on this state tree, and thus we can show a command line interface and we can show a web interface. So from this current state, we produce a matrix, and then we take that matrix and we pass it to toString. So what we do is that we produce the matrix, and then immediately we turn that matrix into a string. So actually, I mean, maybe you could argue that I've made it unnecessarily complicated in some way, and maybe we should find a way which is more similar to the web approach, where we sort of just immediately do display what we want to display. But to me, this seemed like the easiest approach, like having this intermediate data structure that's this matrix-like thing. Because I mean, if you think about it, we print this pretty much as a matrix, right? Like this has a number of rows and it has a number of columns. And actually, if we look at toString here in the matrix module, you can see that this is where it becomes obvious that it's fairly trivial, because toString takes, I wrote XSXS here because like usually in functional programming you will see people say like XS or SS or something like that to indicate that you have an array of something. So you have an array of XS here. But I tend to write XSXS. I'm not sure if that's conventional. I hope that's conventional because it seems sensible to indicate that it's an array of X's. So, and that's why I say XSXS here on the outside and then XS here on the inside. So the way this works is that we map over the outer array, and then for every inner array we join up all of the values with a space. If you think about it, you can see here that there's a space in between. There's a space in between all of the different dots. Like if we didn't have that space, probably this won't, yeah, this actually does work, right? This doesn't look very nice, also because columns are a lot narrower than the rows. So we need that extra space in order to sort of make it look a bit more nice. So we join it up with space, and then we join up each of these rows with a /r/n, which is essentially a line break, so that we can print it as a single string that sort of looks like a grid. And actually, I just realized I used to have a 0.5 point-free, or not a point-free version of this, but rather a version that's more similar to the make function here, where instead of actually calling map on the axis of x's, we say map and pass the axis of x's, because I guess that could be more elegant than this. But anyways, there are multiple ways you can rewrite this function, and some of them are probably a lot more elegant than the way I've written it now. But anyways, that's the toString function. And of course, if we think about this method again, like what we were saying is that we first do from state and then we do toString. So we start with this from state and then we do toString. So from state, what that does is that it creates one of these axis of x's. It creates one of these grids or one of these matrices containing the appropriate values. And how we do that is essentially by piping, right? We say, well, we need to pass this state, so we take the state as an argument and then we pipe it through a few functions. But the first function makes the matrix, the second function adds the snake to the matrix, the third function adds the apple, and the fourth function adds a crash, if there is supposed to be any crash. So again, these are sort of immutable methods in order to just to keep my head straight in this. So matrix.make, we can see up here, right? The matrix.make, here I called it table and not state, because a table is anything that has columns and rows. But I mean, actually what we will pass is, we will actually pass the state, but since we only care about the columns and the rows, I figured I'd call it table here. And what make does is essentially that we use this helper function rep, right? So if we look at the base library, const rep, here we have the implementation of rep, and what rep does is that it takes a constant and then it takes an n, and then it maps this constant using the function k, which is the const function, over the range from 0 to n. So this sounds a bit bonkers, but what this actually means is that if you have, actually let's jump into Node and let's look at this. So const base is require, right, and then we have the base library, and then we can say base dot rep, and if I say a and then I'll pass 10, you can see that we get 10 A's. If I get past 3, we'll get 3 A's, right? And if I, instead of A, if I have 1 here, I'll essentially get an array with this thing repeated the number of times as the second argument that we're passing. And rep was implemented in terms of range, and what range does is just that, let's see if I can remember the syntax. If we do this, right, then we get a range from 10 to 20. We get an array of all the elements of 10 to 20. So what we were doing is that we were mapping over that range in order to have an array of multiple elements. And what we were mapping is that we were mapping the function k of the constant that we were passing. So when we did base.rep a10 here up in the beginning, for example, then our constant is a. So if I say k of a, then I have, oh sorry, base.k, then I have a function that accepts an argument, but it doesn't care about which argument it's passed. Regardless of what argument is passed, it's going to respond with a. And that's how we can, when we map, so actually let's do that manually. Like if I have that range from 10 to 20, and then I map over that, and if I map k of a, we will replace, oh sorry, base k and base.k, we will replace all of the values in the array with a. And that is essentially the way that rep works, and yeah, I guess range and k as well, and map. But anyways, so that's why we do rep here. So I think it's pretty interesting. I mean, what we do is we repeat the repetition of period, or the string period, over the number of columns that we have in this table. We do that for every row that we have in this table. So that's a pretty concise implementation of making a two-dimensional array filled with dots, right? So that's the first thing we do. We make the matrix based on the state. We make the matrix from the state. But then here we have these three functions that we want to use to add additional things to this matrix. We want to change we want to adjust particular cells in this matrix. And note how we're passing state to these, because essentially this one only requires the state to be passed once, but these actually require the state to be passed twice. So we'll invoke them like this. So add snake is a method that can be defined only when we know what the state is. And this, I mean, I was struggling a bit with this. I think this didn't turn out super nice. So if you have any suggestions of how to rewrite this properly, super interesting if you want to post anything about that. I was toying with the idea of probably using the S combinator or converge or something along these lines. But probably we could find out more sensible ways of expressing this. But anyways, what we do essentially is, so add snake, what it does is that when given some state, it will produce a function that's essentially a pipeline where we spread the mapping of setting x, or rather I should say spread the result of mapping the value x over the snake. So essentially, let's think about it. I mean, this looks a bit hairy, but actually it's not that strange. I mean, so the thing about it, like the snake in the state is an array. It's an array of positions. So what we do is that we map the function of setting x, and setting x in the matrix takes a particular position. And so by mapping that, we get a list of functions that we then spread over this piping. So we spread it into arguments. So we make a function that when passed a state, will run that state, not when past the state, when past a matrix, will run that matrix through a bunch of matrix.set transformations that sets x at that particular position. And if you look at set, I mean, set is also fairly straightforward. What it does is that it takes a value and then it takes a position. And what it does then, so the position is then a point, right? Maybe I should have said point. So something that has an x and y. And it calls adjust on the y, or adjust at the y position, but then passes the adjustment of the x position of the constant of the value. So what we do, if we express this in a less strange manner, actually, what this is that we're saying, if we would do this in a mutating fashion, what it does is that it takes another argument because it's point free, right? So it also takes the matrix. And what we do is that we say the matrix of position y and then position x is equal to the value, and then we return the matrix, and then we return the matrix. So that's essentially what the set method, what the set function does. But now we're mutating, and so now we're trying to do that without mutating. And when doing that, we also got rid of the matrix variable here. And of course, adjust is a function that we defined here in our base helper library. But of course, it's also available in a lot of different libraries. And what adjust does is simply that it takes an n, which is an index, it takes a function, and then it takes some kind of collection, some x's. And what it does is that it runs the function at the index n of the x's, right? So it's a way of, if we go back here, right? Like if we say list index equals value, or more specifically, if we say if we run a function over the value at that index, right? That's what this version of adjust does. And then we pass k here because we're not actually interested in running a function over the value. We don't care about the old value. We just want to replace it with a new value. So that's kind of a general version of adjust. And yes, so this we do in order to so essentially what set does is that when given a value, when given a position, and when given a matrix, it produces a new matrix that looks like the old matrix, but where the value at the position has been updated to the new value. And that's essentially what we do with set, right? And so that's why we use it in add snake, and we also use it in add apple, and actually not add crash, because here we did a more simple implementation, I guess. But yeah, that's how we use it in add snake. The way we use it in add apple is much more simple. Then we just simply say matrix.set, and we set to an O at the position of the apple, right? So state.apple contains a position, and we're just saying matrix.set at that particular position, right? So this we could change to an A, and then if we run, you can see that we now have A's instead of O's that represent the apple. So that's the apple. And then the crash is very simple. Here we just say that, okay, if the snake length is 0, in other words, if we don't have a snake, if we've crashed or if we just started the game, then we map the mapping of the constant dash. So over this grid, think about it, the grid is a list of lists. So over every column or row, depending on which order we structured it, I think maybe it's row. So over every row we map, but we map the function that is the mapping of every column. And over that we map the function k, which is constant, that returns, regardless of what it gets, returns whatever we passed it. And what we passed it in this case happens to be this dash symbol, or this pound sign, this hashtag. And that's only what we do if we don't have a snake, so if we've crashed. But if we hadn't crashed, then we pass ID. And why do we pass ID? Because ID is the identity function. So that means that, well, if we haven't crashed, then the grid needs to stay the same. If we didn't do that, let's say we did this in both of the cases. So instead of doing ID, we do this mapping again, then it'd be a constant crash. Like it looks like constant, but we're actually just redrawing this constant and recomputing this constant all the time. But yeah, so that's why we need to pass the ID. And if we didn't do this mapping of pound, that wouldn't be the end of the world. It would just not be obvious when we've crashed. So what we want to do is visualize, like we did in the web, right? Like here, when we crash, we have the screen sort of turns red like that, right? And here in the terminal, we want every position to be replaced by a dash. And that's that, right? So these are the matrix operations that we have. We can make a matrix, we can set something in the matrix, we can, given some state, produce a function that, when given a matrix, adds that snake to the matrix. Similarly for the apple, and similarly for a crash. And then we can take a matrix and turn it into a representable string. And then here we have the from state function that essentially first makes a matrix, adds a snake, adds an apple, and adds a crash, all in order, so that we can simply just call that from over here in our game loop when we want to show. Okay, that's show. Then we also have step, but step is super trivial. Similarly, if we go up here into the top, like similarly to the web, right? Like if we go back to web.html, you can, web.js, you can see here in the top that we have this mutable state, where we say that the state is equal to initial state. For some reason I chose lowercase s and uppercase s here. That makes no sense. But in the CLI here, we have a variable called state, which starts as the initial state from the snake, and that is the immutable state. And the reason that that's mutable is, of course, that we need to listen to these key events. So I'm not gonna bother you about how this listening to keys work, but this seems to be like the way we do it in Node when we want to listen to key presses. So we capture what's in standard in, and if we happen to press Control-C, we need to exit the process because people need to be able to exit the program. But if not, then I'll just do to upper on it, so we don't have to worry about lowercase w or uppercase w, and then we just look for WASD, as in the web case, right? And HJKL, and we look for up, left, down, right arrows. And what we do is actually the same thing. Let's look at this. So yeah, so the state is equal to the enqueuing of the old state and the new move, and then we break. And this is the same thing as we had here in the web, where we said, okay, enqueue based on the new state this new move, and compute a new state from that, and replace the mutable state with this new state that's computed. And that's the way we do that. And yeah, I guess that's pretty much it. So to do that read line, we needed to read in the base node library read line. It seems that there are other ways of doing it, but this seems to be the easiest way. So yeah, it kind of seems like that's it. It seems like a lot of code in some sense, right? But if you think about it, what I would argue is that what we've done is that the snake implementation is actually only this file. It's actually only snake.js. Like this is the implementation of snake. The other stuff regards how to display the snake game, like what graphics version or engine you want to use your snake with, what GUI you want to use your snake game with. So which way you want to display snake to the user, and which way you want the user to interact with your snake game. So again, like if we think broader than game programming, functional programming is really susceptible to modularity. And so what I mean is, when you produce small functions, you can really quickly feel how they become very composable and very reusable. But yeah, I mean, but if you actually know exactly what you're building and you know that you're not expecting any change and you have a strict specification, then yeah, maybe you don't need to be worried about change. But if you are worried about change, like if you're building an application that might change over time, or if you're building something that might be shipped to multiple platforms, then approaching something even like game programming, kind of like we've been approaching it today, I think actually makes a ton of sense. What do you think? Let me know in the comments and let's discuss. Beyond that, if you thought this was interesting and if you want me to decompose any other games, let me know, like Tetris or Pong or whatever. I mean, shoot something in the comments. Either way, clearly this code can be improved a lot, but hopefully you find something useful as we dove through this piece of code. Hey, I'm Christopher. I'm the guy that you just saw in this video. I hope that you liked the video, and I really hope that you felt that you learned something. If you did like the video, I would suggest that you check out my YouTube channel. The link to my YouTube channel is in the description. So, thank you again very much for watching, and I hope to see you in another video either here on this channel or over on my channel. I'll see you in the next one.